Hello everyone, in this video I will explain how to obtain voltage and current reference that has a positive temperature coefficient. By positive temperature coefficient I mean that if you have a voltage or a current, then those are proportional to the temperature, and the coefficient of the proportionality, in this case the alpha, is greater than 0. Such voltage or current reference we will call a PTAT. Same if you have a current with alpha positive, that would be a PTAT current reference. First, let us recall the formula that relates the current and the voltage of a diode. So if you have a diode, and the voltage we will denote by VD, the current inside we will denote by I, then it is known that the current that flows inside the diode, I, is equal to the reverse current, IS, times exponent VD over VT. The actual formula is a bit more complex. There is also exponent VD over VT minus 1, but for simplicity we will assume that VD is much larger than this VT voltage, and if that is the case, then the exponent would be bigger, much bigger than 1, and so we can drop the 1 in this formula. So we can instead simply write that the current is equal to reverse current and this exponent times this exponent. The VT here is the thermal voltage, and it is equal to K times the temperature divided on Q, where the K is the Boltzmann constant and the Q is the charge of the electron. In this formula we immediately notice that this thermal voltage is actually proportional to T with the coefficient K over Q, and the K over Q is a positive constant. So in fact the thermal voltage is a PTAT reference voltage. So now let us look into the following circuit. So we have one diode here with some current that flows in, I, and we have n copies of that diode here. Connected as follows, and let's assume that the same current that flows in this left diode flows into here, which means that if we have n diodes, then each will see only the I over n current. And let's assume that this is just a ground here. So we will denote this as VD, so let's denote them as, this is the diode D, this is the diode 1, diode 2, and diode N. The voltage of this diode on the left we will denote as VD, and these ones they share the terminals. Therefore, we can just denote this voltage here as VD1, because since they share the terminals, then the voltage on D2 and D3, etc. to Dn is also equal to D1, so we can just denote this as VD1. We will discuss, of course, how to send this current, equal amount of on current on this diode D, and also same current to these N diodes that are connected together. But for a moment, let us look to the formula that relates the current and the diode voltage on the for the left diode. So we have that I is Is exponent Vd over Vt, and the current on the D1 diode would be I over N, since these are the same diodes, and the full current that flows into all these diodes is I, then each will see I over N. So I over N would be equal to Is times exponent, and the voltage we denote it as Vd1, Vd. Now this we can rewrite as follows, that I is equal Is times N exponent Vd1 over Vt. Now let us express the Vd and Vd1 in terms of this current I. So we have that the Vd equals I divided, so first we divide I on Is, and then we take a logarithm. So we will have logarithm I over Is, and then we multiply by Vt. So we will have that Vd equals to Vt log I divided on Is. And the same we do here. We will obtain that this is equal to Vt log I divided on N times Is. Now we take a difference of Vd and Vd1, and we obtain that when we subtract two logarithms, we can instead just consider just the division of the arguments. So we will have logarithm I divided on Is, divide this on this argument, which is just the same as to multiply with the reverse of this. And we notice that we can cancel the I in the numerator, and the same the reverse current. So we simply obtain that Vd minus Vd1 is equal to log of N times Vt. And here we notice that the N was just the number of the diode, so log of N is a constant, and Vt was the terminal voltage, which, as we said, was a PTAT voltage reference. Therefore, the Vd minus Vd1 is also a PTAT voltage reference, because if we write it, it would be log of N times K over Q times T. So this would be the coefficient which is greater than 0, and therefore Vd minus Vd1 is a PTAT reference. Now let's discuss how we can send the same current on this diode and the same amount of the current I on the left diode and the same amount of current to these N diodes that are on the right. So we can just use a current mirror like this, two PMOSes that share the same gate. So we connect the, let's call them M1 and M2. We connect the drain of the M1 to the diode D, and the drain of the M2 to the diodes D1, D2, Dn. And this is the ground. So this is the D1, D2, etc., Dn. And this is the supply, which we will denote as VDD. So now if we forget about the channel length modulation, because of the channel length modulation we will have slightly different currents on the left and on the right. But if we forget about it, then the currents due to these current mirrors on the left, so this is a current mirror of 1 to 1, which means that the W over L1 of the M1, the width on the L for the M1 is equal to the width W over L for the second one. Then the currents would be equal. So we will have I, and we will reach to our configuration here, where we had currents on the left and on the right equal. Now, in this case, as we said, the VD minus VD1 would be a PTAT reference. So this is the VD, this is the VD1, so this is the VD1, this is the VD, and VD minus VD1 would be this difference. So we can say that the differential voltage between the left and the right wings is the difference of the voltages between the left and the right, VD minus VD1, so this is the VD minus VD1, is a PTAT reference. And in the next video, we will continue exploring PTAT references and build a PTAT voltage reference with respect to a ground, not a differential one, but with respect to a ground. Thank you.